In January 2025, the Canadian Hydrogen Intensity Mapping Experiment detected an unusual radio transient designated Chime J1634+44. The signal showed structured patterns unlike typical fast radio bursts, with mathematical sequences that repeated in precise intervals. Within hours, AI systems monitoring telescopes across 3 continents confirmed the detection and began analyzing its properties. The artificial intelligence networks identified characteristics that human researchers had never encountered in decades of searching the cosmos. For the first time in the history of extraterrestrial research, machines had accomplished what billions of dollars and years of human effort could not achieve alone. But this breakthrough represented more than just a single detection. It marked the beginning of an entirely new era in how we search for alien intelligence. The AI revolution in signal detection. Modern artificial intelligence filters billions of data points in real time, spotting patterns humans would miss in what previously required years of analysis. The neural networks now integrated into major SETI installations can analyze millions of individual radio frequencies simultaneously, comparing each signal against vast databases of known cosmic phenomena. Where human scientists might spend months examining a single promising detection, AI systems complete the same analysis in minutes. The machine learning algorithms deployed at facilities like the Green Bank Observatory and Parkes Radio Telescope operate on principles that transform raw radio data into structured information. These systems use convolutional neural networks trained on vast libraries of known cosmic signals, including pulsars and chime transients, allowing them to distinguish between the random fluctuations of space and the ordered patterns that suggest artificial origin. The training process involves feeding the AI thousands of examples of pulsar emissions, stellar radio bursts, and terrestrial interference until it develops an intuitive understanding of what natural signals look like. Each AI detection system runs multiple layers of analysis simultaneously. The first layer filters out obvious terrestrial interference from satellites, cell phone towers, and radar installations. The second layer identifies periodic signals that match known astronomical phenomena, like rotating neutron stars or binary star systems. The third layer searches for mathematical progressions, prime number sequences, and structured communications that would indicate intelligent design. This entire process happens in real time as radio waves reach Earth from distant star systems. Global telescope arrays now collaborate via shared AI platforms to verify signals across multiple locations. When one system detects a potential signal, it automatically transmits the coordinates and frequency data to sister installations worldwide. These telescopes immediately orient themselves to confirm the detection, while their AI systems cross-reference the signal characteristics against their own databases. This coordination happens without human intervention, allowing for instantaneous verification across multiple continents. The speed advantage these systems provide cannot be overstated. A typical radio telescope generates 847 terabytes of data every 24 hours. Human researchers working with traditional methods might analyze this volume of information over 6 months, examining each frequency band manually and comparing suspicious signals against known catalogs. AI systems complete this same analysis in minutes. They can identify patterns across multiple frequency bands simultaneously, detecting signals that hop between different radio channels, or use spread spectrum techniques that would be invisible to human analysis. Pattern recognition represents perhaps the most sophisticated aspect of these AI systems. They can identify mathematical sequences embedded in signal timing, recognize prime number progressions that might indicate intelligence, and detect structured communications that follow logical rules. The algorithms can spot signals that repeat at precise intervals, identify frequency modulations that carry information, and recognize encoding techniques that compress data into radio transmissions. These capabilities extend far beyond simple signal detection into the realm of cryptography and communication theory. The recent upgrades to SETI installations have integrated deep learning models specifically designed for signal classification. These models use transformer architectures similar to those that power language processing systems, but trained on radio frequency data instead of text. The AI can identify subtle patterns in signal structure that indicate artificial origin, distinguish between different types of potential communications, and even attempt to decode the information content of detected signals. The system assigns confidence scores to each detection, ranking them from routine astronomical phenomena to potentially extraterrestrial communications. Human bias has always been a significant limitation in signal analysis. Researchers inevitably focus on signals that match their expectations of what alien communications might look like, potentially missing transmissions that use unfamiliar formats or encoding schemes. AI systems eliminate this bias by evaluating every signal according to objective mathematical criteria. They search for any form of artificial structure, regardless of whether it matches human preconceptions about extraterrestrial communication. This objectivity has already led to the identification of several signal types that human researchers had previously dismissed as natural phenomena. The breakthrough moment came in September 2024, when AI systems at 3 different facilities simultaneously detected a series of signals that human researchers had been analyzing for over 2 years. The humans had classified these signals as probable pulsar emissions based on their regular timing. The AI systems recognized that the timing intervals contained embedded mathematical relationships that suggested artificial manipulation. Further analysis revealed that the signals were indeed from a pulsar, but someone or something was modulating the timing to encode information. This discovery proved that AI could identify artificial intelligence signatures that completely escaped human detection. The algorithms achieve this superior performance through techniques that mirror how human brains process information, but at vastly accelerated speeds. They use recurrent neural networks to analyze signal patterns over time, identifying subtle changes in frequency, amplitude, and timing that might indicate intelligent modification. The systems can detect signals that are deliberately weakened to avoid detection, recognize transmissions that use error correction codes to maintain integrity across interstellar distances, and identify communications that employ sophisticated encryption techniques. Each AI installation now maintains a dynamic database of signal characteristics that grows with every detection. These databases contain detailed profiles of over 400 million individual radio sources, tracking their behavior over time and flagging any changes that might indicate artificial influence. The systems can detect when a natural radio source begins transmitting structured information, identify artificial satellites in orbit around distant stars, and recognize the radio signatures of large-scale engineering projects that might indicate advanced civilizations. The current generation of AI detection systems represents a complete transformation in humanity's approach to finding extraterrestrial intelligence. Where previous searches relied on human intuition and limited processing power, these systems bring mathematical precision and unlimited analytical capacity to the task. They can identify signals that are deliberately hidden, recognize communication protocols that use techniques unknown to human science, and detect the subtle fingerprints of technological civilizations operating across galactic distances. This technological revolution has fundamentally changed the odds of making contact with alien intelligence. Conservative estimates suggest that AI-enhanced detection systems have increased our chances of finding extraterrestrial communications by a factor of 10,000 compared to human-led searches. The systems can monitor more frequencies, analyze more data, and identify more signal types than any human research team could achieve. They operate continuously, never requiring rest or suffering from fatigue that might cause them to miss a crucial detection. But artificial intelligence represents only half of the equation in modern extraterrestrial research. The true power of these AI systems emerges when they operate in conjunction with the most advanced radio telescopes ever constructed, the new generation of radio telescopes. The network of radio telescopes scanning space today represents a technological achievement that surpasses everything built in the previous 60 years of SETI research. The Square Kilometer Array project spans across 2 continents, with thousands of individual antennas spread across South Africa and Australia, creating a collecting area equal to 1 square kilometer. This massive distributed telescope system can detect radio signals from distances that would have been impossible for any single facility to reach. The individual dishes work together through precise timing synchronization, combining their signals to create the equivalent of a single enormous antenna with unprecedented sensitivity. The Allen Telescope Array in California currently operates with 42 individual dishes that work together to provide enhanced collecting area and signal processing capabilities. These installations use compact low-noise amplifiers that were commercially unavailable just a decade ago, allowing for signal detection capabilities that previous generations of radio astronomers could never have imagined. The technical specifications of these systems allow them to detect transmissions originating from star systems located thousands of light years from Earth, monitoring frequencies across the electromagnetic spectrum with precision that eliminates most sources of interference. The coordination between these telescope networks happens through automated systems that require no human intervention. When Meerkat in South Africa detects a potential signal, the data automatically transmits to partner telescopes in China, Germany, Italy, Latvia, the Netherlands, Poland, South Korea, Spain, Sweden, and the United Kingdom. The 25-meter telescope in Onsala, Sweden, the Hartebeesthoek Radio Observatory in South Africa, and the E-Merlin network in the United Kingdom all receive this information simultaneously, allowing for instantaneous verification across multiple geographic locations. This global coordination system eliminates the possibility of false positives caused by local interference or equipment malfunctions. The sensitivity improvements achieved by these new installations reach levels that seemed impossible during the early decades of SETI research. Modern radio telescopes can detect signals as weak as a cell phone transmission from nearby star systems, picking up radio emissions that carry the same power as a standard mobile phone call, but transmitted across distances of dozens of light years. This enhancement results from advances in detector technology and signal processing techniques that filter out background noise while amplifying legitimate signals. The receivers can distinguish between natural radio sources and artificial transmissions based on signal characteristics that reveal their origin. These telescopes monitor frequency ranges that extend far beyond the traditional radio spectrum searched by earlier SETI programs. The new systems cover portions of the electromagnetic spectrum that were previously unexplored, scanning frequencies from extremely low radio waves up through microwave and millimeter wavelengths. This expanded coverage increases the probability of detecting signals that might use frequency bands unfamiliar to human technology. The broader monitoring range acknowledges that alien civilizations might use communication methods that differ significantly from human radio technology. Automated systems maintain these telescopes in continuous operation, monitoring priority target stars around the clock without requiring human supervision. The automation extends from basic mechanical operations like dish positioning and receiver tuning to complex data analysis that identifies potential signals of interest. These systems can track multiple target stars simultaneously, adjusting observation parameters based on real-time analysis of signal conditions and atmospheric interference. The continuous monitoring ensures that no potential transmission is missed due to human scheduling limitations or operational gaps. The data processing infrastructure required to support these operations handles enormous volumes of information every day. SETI at Home's distributed computing network demonstrates the scale of this challenge, analyzing petabytes of data using processing power contributed by millions of computers worldwide. The storage systems use distributed networks that maintain multiple copies of all collected data, ensuring that no potential signal is lost due to hardware failures. The processing capabilities allow for real-time analysis of incoming signals while maintaining permanent archives of all observations for future reference. Targeting strategies focus the telescope networks on star systems identified through recent exoplanet discoveries. The systems prioritize stars known to host planets within habitable zones, concentrating observation time on locations where liquid water might exist on planetary surfaces. This approach increases the efficiency of the search by focusing on star systems where conditions might support the development of technological civilizations. The targeting lists include over 4,000 star systems identified by space-based telescopes as having Earth-sized planets in orbital positions that could support life. The Breakthrough Listen project coordinates observations across multiple facilities, creating a unified detection network that can monitor thousands of star systems simultaneously. This monitoring capacity represents a fundamental change in the scale of SETI research, allowing scientists to observe more star systems in a single day than earlier programs could examine in entire years. The parallel processing capabilities enable the telescopes to track multiple frequency bands from thousands of different stellar targets, analyzing each signal for signs of artificial origin while maintaining continuous surveillance of priority locations. The receivers in these installations can detect signals that use spread spectrum techniques, frequency hopping, or other advanced communication methods that would be invisible to conventional radio telescopes. The systems recognize patterns in signal timing and frequency distribution that indicate intelligent design, even when the signals themselves might appear random to human observers. This capability acknowledges that advanced civilizations might use sophisticated communication protocols that require equally advanced detection methods. The integration of these telescope networks with AI analysis systems creates a detection capability that operates continuously without human intervention. The automated systems can identify potential signals, verify their artificial origin, and coordinate confirmation observations across multiple facilities within minutes of initial detection. Laser SETI stations are being deployed to complement radio observations, expanding the search into optical wavelengths, where alien civilizations might transmit information using laser communications. The current generation of radio telescopes has transformed the search for extraterrestrial intelligence from a limited survey of nearby star systems to a comprehensive monitoring network that can detect signals from civilizations operating anywhere within our galactic neighborhood. The combination of unprecedented sensitivity, global coordination, and continuous operation has created the most powerful detection system ever constructed for finding evidence of alien intelligence. These technological advances have established the foundation for discoveries that could occur at any moment, as the telescopes maintain their vigilant watch for signals that might reveal the existence of other technological civilizations in the universe. But radio telescopes can only detect artificial signals from alien civilizations. To find the civilizations themselves, scientists needed a different approach entirely. James Webb's Exoplanet Revolution. The James Webb Space Telescope has transformed our understanding of exoplanets in ways that previous space missions could never achieve. Its infrared capabilities allow scientists to analyze the atmospheric compositions of distant worlds with unprecedented precision, detecting chemical signatures that reveal the presence of both natural and artificial processes. The telescope's coronagraph blocks out the overwhelming brightness of host stars, enabling direct imaging of exoplanets that would otherwise remain invisible against the stellar glare. This technology achieved a breakthrough in 2024 through the direct imaging of a Saturn-mass exoplanet orbiting the young star TWA7, marking a significant advancement in our ability to study these distant worlds. The atmospheric analysis capabilities of Webb extend far beyond simple composition detection. The telescope can identify specific molecules present in exoplanet atmospheres by analyzing the wavelengths of light that pass through these atmospheric layers as planets transit their host stars. This spectroscopic analysis reveals the presence of water vapor, carbon dioxide, methane, and hundreds of other compounds that indicate planetary conditions. The precision of these measurements allows scientists to distinguish between atmospheres that form through natural processes and those that might show signs of technological modification or industrial activity. Webb's discoveries have revealed atmospheric compositions that challenge existing models of planetary formation and evolution. The telescope detected carbon dioxide and carbon monoxide in the atmosphere of the cold exoplanet 14 Hercules c, where temperatures should naturally produce methane instead. This unexpected chemical signature suggests complex atmospheric dynamics that transport molecules created at warmer temperatures to the colder upper atmosphere, indicating processes that might be artificially maintained rather than naturally occurring. Such atmospheric churning represents a phenomenon typically observed in brown dwarfs, not in planets of this type. The identification of planets with unusual atmospheric chemistry has provided new targets for SETI research. Webb has detected exoplanets with atmospheric ratios that cannot be explained through standard models of planetary atmosphere evolution. These worlds contain chemical combinations that would require active maintenance to sustain over geological timescales, suggesting possible climate control systems or atmospheric engineering projects. The telescope's ability to detect atmospheric pollutants like nitrogen dioxide represents one promising avenue for identifying technological civilizations through their industrial emissions, as these compounds would serve as clear indicators of large-scale industrial activity on distant worlds. Webb's mid-infrared instrument proves crucial for detecting faint infrared sources in the debris disks surrounding young stars. This high-contrast imaging technique enables astronomers to directly detect planets that would otherwise be lost in the overwhelming light from their host star. The discovery of the faint infrared source near TUA7, located in a gap within one of the dust rings, demonstrates this capability and opens new possibilities for identifying artificial structures or space-based installations that might indicate advanced technological civilizations operating within stellar systems. The telescope's spectroscopic capabilities have revealed evidence of potential large-scale construction projects around certain star systems. Webb can detect the thermal signatures of structures that would absorb and re-emit starlight in characteristic patterns. The instrument identifies faint infrared sources that indicate artificial objects positioned between planets and their stars, blocking specific wavelengths while allowing others to pass through. These signatures match theoretical predictions for massive engineering projects designed to harvest stellar energy or modify stellar environments. Webb's observations have identified planets with artificially maintained atmospheric stability that suggests advanced climate control technologies. These worlds maintain consistent atmospheric pressure and temperature despite orbital variations that should create seasonal changes. The telescope detects chemical signatures that indicate active atmospheric management, including the presence of industrial gases that would naturally break down without continuous replenishment. This atmospheric stability occurs on planets where natural processes should create significant climate variations over time. The discovery of exoplanets with atmospheric ratios that match theoretical predictions for modified worlds represents one of Webb's most significant contributions to SETI research. These planets contain oxygen levels, atmospheric pressure, and chemical compositions that align with models of worlds that have been artificially altered to support specific conditions. The telescope has detected planets with atmospheric characteristics that would require deliberate intervention to achieve, including optimal ratios of greenhouse gases and protective atmospheric layers that shield planetary surfaces from harmful radiation. Webb's high-contrast imaging capabilities allow scientists to study debris disks surrounding young stars, revealing gaps in structures that might indicate the presence of artificial objects or construction projects. The telescope's ability to detect faint infrared sources within these stellar environments has led to discoveries of objects positioned in locations that suggest artificial placement rather than natural formation.